Hello and welcome back to the AQUARIUS software training video series on rating development. One of the key aspects of developing a good rating curve is our interpretation of field observations, particularly with respect to control conditions. This presentation is designed to help with this interpretive analysis. We will lead into our discussion on controls with a review of basic hydrodynamics. We'll describe what a control is, the difference between a section control, a channel control, multiple control conditions, and controlling forces. We like to think of our stage-discharge relation as a hydraulic relation, and the reason for that is very good, because if we're dealing with a hydraulic relation, then we know it will plot as a straight line and a log-log plot, which greatly improves our ability to interpret rating curves. Now, in order to do that, we have to examine our basic assumptions. One is the uniform flow assumption. So for the uniform flow over the length of the control reach, we need our flow lines to be parallel. So we need to examine that assumption. We need to look at our steady flow assumption, that the flow is constant from time to time. Over the timestamps that we're monitoring and measuring discharge is a flow constant. So another thing that we need to look at is our ability to translate stage to pressure head information. So we're assuming that stage is a good index of what the total energy in the stream is, but that may not always be the case. So we need to examine that assumption very closely as well. There are some really important implications to these assumptions in our interpretation of rating curves. One is that the steady and uniform flow assumptions tell us that the force in the downstream direction is equal to the resisting force. Our assumption that we can relate stage with the total energy in the stream tells us what that downstream force is, and then we can make observations about the channel configuration to understand the resisting forces, and we can develop an understanding of how those resisting forces will change as a function of stage, and how those those factors affecting the channel resistance can be lumped into our rating curve parameters. So what are these forces resisting flow? In this equation, we have the friction head is equal to a constant times the square of the velocity times the wetted perimeter times the length of the channel. So this constant is actually a lumped parameter. It includes things like channel rugosity, the sinuosity, the cross-sectional shape, obstructions in the channel, as well as attributes of the water itself, the density and the kinematic viscosity. So what is a control? A control is the sum of all of the terms in the friction equation, including those in the constant lumped into the constant K. Channel control is when the channel length and the wetted perimeter are the dominant terms in the equation. And a section control is a special case where the velocity is a dominant term in the equation. The specific energy curve gives us a mapping, an envelope curve of all the possible energy states any stream could have. This is the sum of the pressure potential energy represented as the depth, and the velocity head energy, this v squared over 2g component. The velocity head component can never be negative, and so we have this curve to the right of that one-to-one line drawn between depth and specific energy. At a Froude number of 1, we have a velocity head component that is exactly 1/2 of the pressure potential energy component. This is a minimum on the specific energy curve. As that section control gets drowned out, as the water gets deeper, then we move into a channel control situation, and the channel control is downstream of the gauge. If we have a higher velocity component, then we get into that where turbulent water with a fluid number greater than 1, and the velocity head starts to dominate the energy in the stream. And the channel control may actually be upstream of the gauging location. We've been talking about the Froude number. The Froude number is the ratio of stream velocity divided by the square root of gravitational acceleration times channel depth. Where you have a Froude number equal to 1, we call that critical flow, say over the crest of a weir or over a riffle. And that makes a really good situation for gauging, because stream velocity is directly proportional to channel depth. And so you have can have a very stable Weir equation. Where the Froude number is greater than 1, you have turbulent flow or standing waves, and that's a very poor section for gauging. And part of the reason is where you've got turbulent flow, by definition, your flow lines are not parallel, so you're already in violation of your assumption of uniform flow. And there's other reasons why turbulent flow makes for a poor gauging section. Froude number less than 1 is tranquil flow, and generally tranquil flow situations are good for gauging. You can test whether the Froude number is less than 1 by tossing a pebble in the stream, and if the ripple from the pebble propagates upstream, then you know you've got a Froude number less than 1. When we're talking about a section control, we're talking about a situation where the gauge is immediately upstream of a location in the stream where the Froude number of the flow is equal to 1. Now, if you look at these two examples here, we do have flow over an obstruction and through a convergence zone where we do have critical flow, but these would not be good gauging locations, because in these cases you have convergent flow lines. So we're in a situation here where we're in violation of our assumption of uniform flow. What we're really looking for section control is someplace where you have a level gauge pool so that there's zero approach velocity to the control feature. In that way, the stage that's measured less some offset gives you a direct measure of the depth of water over the control feature. That's really what we're looking for. And so if in these situations where you have a non-zero approach velocity, you're actually getting into something that is more like a supercritical flow situation, which is certainly not ideal from a gauging perspective. When we're doing site reconnaissance, we're always looking for a level pool with the discharge controlled by a natural section control feature like a rock ledge. So this location looks promising. I'd be a little bit concerned about the velocity approaching that rock ledge. I'd also be a little bit concerned about more than a little bit concerned about the shallow banks and the complex geometry and what that's going to look like at high water. So if I was doing this site reconnaissance, I might want to keep looking. However, it might be the best we can find on this stream. When the Froude number is less than 1, we're generally talking about a channel control. This is where the pressure potential head is a dominant force driving flow. And what we have to consider is a total of the resisting forces along some length of the channel. And this length can extend for some distance downstream. And so we need to consider the wetted perimeter, the sinuosity, rugosity, channel shape, and obstructions of the along that length. The exponent of a channel control would generally be expected to be somewhere around 1.67 for a perfectly rectangular channel, but could be higher if the width varies very much with channel depth. Where the Froude number is greater than 1, we're talking about supercritical flow. This is where the velocity head becomes a dominant form of energy driving flow. Now in this situation, no information from the channel downstream of the gauge can propagate upstream. So our actual control section might be upstream of the gauge. The exponent of the rating equation could be greater than 2.5. And so these are not great gauging locations for a number of reasons. One is it can be very difficult to maintain gauging equipment in a turbulent flow regime. It can be very difficult to monitor stage. There's a lot of noise in the stage signal. There can be a lot of aeration of the water, so our density, our assumptions about water density become invalid. But more fundamentally, we've got a violation of our assumption of uniform flow. In turbulent water, the flow cannot be uniform. So these are not great gauging locations, and we would choose to avoid them, but it's not always possible. And even some gauges that are really good gauges through most of the range of the stage, at flood stage may become turbulent. And so if we know what stage the stream transitions from tranquil to turbulent flow, we can expect a break in the slope of our rating curve at that point. One of the things that I always find very satisfying about my work in hydrometry is how well our very simple hydraulic relation, our rating equation, works for so many streams all over the world, over such a wide range of stage for very different streams. So, and this is because unconfined alluvial streams are self-organizing systems that conform to the least action principle, and they trend toward the maximum flow efficiency. So our streams have energy, and they use that energy to rearrange themselves using fluvial geomorphological processes to transport sediments and deposit sediments. The streams are constantly aggrading where they need to aggrade. They degrade where they need to degrade. And this creates it's this channel maintenance that creates this conformance to our assumptions necessary for use of our rating equation. However, there's many forces working against maximum flow efficiency. There's geological features, biological features, and so on. So it's things like large woody debris in small channels. It's things like relics of hydrological events, like large boulders in the stream. It's things like rocks that resist erosion. Those are the sorts of things that create our multiple control situations. We can create a hypothetical multi-control scenario where you have section control at very low flow, you have critical flow over stream bed cobbles, and then as those cobbles become submerged, you get into a channel control situation where the control on the flow is the attributes of the channel downstream of the gauge, and then high flow events where there's just so much water from basin runoff that this water just overwhelms the channel capacity and creates a supercritical flow situation where velocity head becomes a dominant term controlling discharge. There's a number of problems with overbank flow, starting with that. When you get into water flowing through terrestrial vegetation and those sorts of things, a lot of our assumptions that we're using in developing our hydraulic relations becomes somewhat suspect, to say the least. We generally are under-equipped to be able to get the measurements to define the range of stage for overbank flow to really define what the shape of the curve is. And so unless you do have some measurements, unless you are able to use perhaps indirect methods such as a slope area method to recreate flows as stage discharge measurements for overbank flow, it's generally a good idea to not extend your hydraulic relation above bank flow level. When we're evaluating channel controls, we need to consider some of the other factors in the head loss equation. One of these is rugosity. refers to the roughness of the stream bed and the stream banks, say due to large woody debris, bedrock, boulders, rocks, down to sand, silts, and clays. And so this we know from basic hydrodynamics that this roughness factor is going to be captured in the coefficient of the rating curve. And so if you have, but really what we're talking about is a composite roughness. You may have a different roughness in the stream bed than on the stream banks. And so as the stage rises, your composite roughness changes. And if this transition from one roughness, one composite roughness value to another composite roughness value is fairly abrupt, you may need to have a break point in your rating curve, where you might, if your stream bed is particularly rough, you might need the curve to be plot a little bit further to the left at one stage, and then above some threshold you might need the curve to plot a little bit further to the right if your stream banks are less rough than your stream bed, for example. But in many streams that are more self-organizing, this transition in roughness is going to be gradual. And so you're not going to have a discrete breakpoint in the curve. What you're going to have is a curve that wants to be, say, further to the left at low stage and, say, further to the right at high stage. And that tendency, that change in roughness with respect to change in composite roughness with respect to stage is going to be captured in the exponent of the rating curve. It's going to change the slope of the curve. Another one of the factors from the head loss equation that we need to evaluate when we're considering channel controls, sinuosity. Sinuosity refers to the meanders in the stream channel. It is generally only relevant when we're talking about a very tranquil stream where the channel control length extends some distance downstream, encompassing one or more meanders. This factor is going to be apparent in the coefficient of the rating curve, but we need to pay attention to whether the length, the controlling length of the channel changes as a function of stage. And if it does, and this length of the control at different stages encompasses more meanders or fewer meanders, then that effect is going to get translated into the exponent, changing the slope of the rating curve. Without a doubt, the most important factor from the head loss equation is channel shape. This is the cross-sectional shape over the length of the controlling reach. And so this has a profound effect on the exponent of the rating curve because it controls the amount of area available, cross-sectional area at any given stage, which is directly related to the specific weight of water, the mass of water available at any given stage to drive flow. Channel shape also affects the position of the relative position of our point of zero head and our point of zero flow, and that can change as a function of stage. So where you have a more complex shape, you're not going to have a constant point of zero head. So the channel shape can also be very dynamic. It can be affected by geomorphological processes, channel aggradation and degradation, and biological processes such as weed growth and large woody debris and those sorts of things. Channel shape in many natural channels does not mean that you've got a steady increment of cross-sectional area as a function of stage, as shown in these two pictures from the Murray River, where you've got where the channel shape actually closes in on itself at higher stages and then spills over and gets into overbank flow. So in this kind of with this kind of cross section, you're going to have a very complex rating curve. Another thing that we need to consider when we're developing rating curves for natural channel controls are any obstructions that occur anywhere along the length of the controlling reach. These may be man-made obstructions or natural. And they may be in effect only over a certain range of stage, or they may be only in effect over a certain period of time. We need to develop a pretty good understanding of how these obstructions are going to influence the parameters of our rating curve. The physical properties of water are also considered in the head loss equation. These include density and kinematic viscosity of the water. And these both change as a function of temperature and sediment load. If a stream always has a high sediment load at high flow and a low sediment load at low flow, then you can expect that this change in density with respect to stage is going to be captured in the exponent of the rating curve. If the pattern of sediment loading is not consistent with respect to stage, then you might expect to see more scatter. High sediment load increases viscosity, which increases drag in the laminar layer, thus altering the shape of the vertical velocity profile. So if your measurements do not explicitly account for this change in vertical velocity profile, if the vertical velocity profile is assumed rather than measured, then you're going to see more scatter in the plot of your points around your rating curve. Another variable in the head loss equation that we need to pay attention to is velocity, or more importantly, velocity squared. So this becomes problematic for us when the Froude number is greater than 1, when you get a significant portion of the energy of the at the control reach provided by what's happening upstream. Now we have no measure of what's going upstream. All we're measuring is the stage at the location. So this creates a lot of uncertainty for us in developing rating curves. We try to avoid doing gauging in these velocity-dominated streams, but sometimes it's necessary, and you need to be aware of how that's going to be affect your parameters in your rating curve. Another one of the variables from the head loss equation that we need to pay very close attention to is wetted perimeter. This is related to things like channel shape and channel rugosity, but it's much more than that. It has to do with the surface area in effect over the length of the control reach. Things like ice dramatically change the wetted perimeter, the contact area of the water with an unmovable solid. So things like vegetation change the wetted perimeter quite dramatically. And these vegetation effects can be quite dynamic as grass grows up at low velocities. There may be quite a high wetted perimeter to weeds and grass from the stream bed, but at higher velocities, that grass is going to bend over and lay flat, and it's going to present a much lower wetted perimeter. As the stage rises up and the water gets into riparian vegetation and starts to flow around the stems of woody plants in the floodplain, that's going to create a very dramatic change in wetted perimeter. We need to pay attention to wetted perimeter very closely. We've referred to the length of the channel control in talking about each of the other factors in the head loss equation. The length of a control section can be very short if it's a section control, or very long if it's tranquil flow. This length dimension of the control feature changes as a function of velocity, which in turn changes as a function of head. So we've got this built-in relationship between stage and the length of the control. So this built-in relationship is going to be apparent in the exponent of the rating curve. I would hope that we've been able to develop an improved understanding of what a control is, a natural channel control, be it a section control or a channel control. And this improved understanding should help you be able to take your observations from the field. What you see, what does the channel look like and be able to interpret those observations in the context of what you're seeing in the rating development toolbox. Hopefully this lesson in natural channel controls will help you to translate your field observations from your field visits into interpretation and analysis in the rating development toolbox. However, that's valid for interpretation and analysis of a curve at a point in time. But how are we going to handle these changing dynamics as they change through time? For that, we'll look to the next lesson on channel dynamics and shift corrections. Here are some links to some very good online self-guided learning resources that may help you to consolidate what you've learned in this lesson. Thank you.